Okay, we're just picking up after the quiz, so really nothing new on the website. I will be, besides new videos, I will be putting up another homework assignment. Today was just a fairly blur so far of activities, because I'm working across multiple domains right now with students, and between graduate students and classes I stay pretty busy. But we had our special faculty meeting for ABET assessment, which is important. It just lets you know that we have to do that every semester with certain classes, get analyzed and assessed, and we debate them, and then we have the report on record for ABET, and that should make you feel better that the degree is keeping its end of the deal up. We made an important vote today too on something we don't want to do anymore, and that is we want to not partake in the BI and electrical engineering anymore. We get so few students, and the pain that we have to go through just to manage them. And everybody knows what the BI program is, right? That's another program. Yeah, Bachelor of Innovation, which has options in CS, electrical, game design, and then there's other BI things all over the campus with a different emphasis, but they're still called BI. But we got it accredited by ABET for like 2 students over the past 3 or 4 years. I mean, we just don't get very many students, and we decided it's just not worth the energy, because everything you do takes energy, right? And that's just another thing that we all realize. So getting on with things, we started talking about Fourier series last time, and I hope to get through all of that today. And so your next homework assignment will have Fourier series related review type problems, and then it will probably have Fourier transform review type problems. And the Jupyter notebook that I have for chapter 2 has examples and activities that do that. Lab 2 in the lab itself delves into Fourier series and power spectra. We're going to do something new though after we get through Fourier transforms. We'll get off into a new topic, autocorrelation and power spectra, which we also touched upon in modern DSP, but only for the discrete time domain. And Chris, you were in the class. Remember, we had random signals, and then we did power spectra. We're going to look at it for deterministic signals, and autocorrelation will be looked at too. So that will be something new that comes along, and that is kind of tied in also with the analyzer in the lab. What is it measuring? Is it measuring the power spectrum? And the answer is yes, through an averaging approximation. So there's slight differences between the spectrum that we're talking about. The line spectrum, the spectrum of a Fourier that we get with the Fourier transform is continuous, but may have delta functions in it, and we're going to couple those together. So Fourier will be all under one umbrella, but then the power spectrum is a slightly different twist on things, but that is kind of the ultimate goal, because that's what an analyzer measures. It measures the watts per hertz of bandwidth, or if it's a discrete spectral line, then it's watts in dBm, usually right on the spectral line. So we talked last time about complex exponential Fourier series, and the key thing is we get it through the synthesis equation, which is the top one. That's how you synthesize a waveform from its Fourier coefficients. And then the analysis is the second equation. That's what gets you the Fourier coefficient from the waveform. So it's a pair, synthesis and analysis. And these two morph into the Fourier integral and the Fourier transform, and we'll talk about that a little bit later, but they are very closely related. But this is for periodic signals. So the Fourier series ideas, if you remember, is for signals that are periodic, whereas the Fourier transform formally is for aperiodic signals. Remember last time we talked about aperiodic. You had an aperiodic signal on the second half of the quiz, right? But if we made that periodic, just like in the homework problem, you had the triangle pulse that was made periodic, then it gets a spectral line spectrum as opposed to a continuous spectrum. And those are the things we're going to be working through. So we talked about this last time. Fourier expansion is unique, so the main thing to take away on uniqueness is you don't have to go through this integral to get the Fourier coefficients. If you can get it expanded into complex sinusoids by some other means, that will be equivalent. It's unique. You can't Fourier decompose a periodic signal in any other way except one way, whether you get it by sort of a backhanded way or you get it by doing the integration up here.
Question.
Yeah?
So the EJ omega t, is that an orthonormal basis function?
Exactly.
Okay.
Correct. Or actually in the business of linear algebra, maybe this entered my mind kind of randomly because my brain fires on all kinds of things that get pushed in there and they pop out when I don't really want them to pop out, but they just show up. So I remember a concept called CON, complete orthonormal set is what it would be called. Complete means it represents anything and everything. So a CON set is what I remember from an advanced linear algebra course I took when I got my doctorate, is really what we have. It can represent everything because it expands with coefficients out to plus and minus infinity. So it can expand anything. But there's other basis functions out there. There's Walsh-Hadamard waveforms, which are pulse-type signals, and they're related to the Walsh code sequences, which are part of a cellular standard called CDMA, or code division multiple access. So there's other types of signals you can expand with. So we then introduced the time average operator as just a convenience thing, and that will be continuing to throw or pop up just as a convenience. But again, the blue boxed equation just tells you what it represents. And of course, if it's periodic signal, then it's what I drew the blue box around for a periodic signal. But it can be a waveform, or it can be a function of the waveform. So it has multiple uses. So if you use it to find the Fourier coefficients, you get this expression right here. And this would be formally the way you might say I'm going to go after the Fourier coefficients. Symmetry properties associated with Fourier coefficients would be that if x of t is real, and that is most of the time in this class, but not always. And I think I've talked about that, but let me just kind of say a couple things about that again. Time was, in the olden days, I guess I'll call it, where everything was analog. We didn't do DSP, we didn't have A to D and D to A converters, and we didn't do software-defined radio. The signal that you would be exposed to is an analog signal, and it would always be a real signal. But nowadays that we do software-defined radio, we get signals that are complex because of the way we process them in the receiver. So it's not always, these 3 points aren't always valid here because sometimes we have complex signals, but still, as a good starting point, this is a good way to go. And if it's a generator you have in the lab that has a single BNC connector on it, or N-type connector, whatever, it's a real signal. How many generators do you see in the lab that have 2 ports that you have to connect to? Like a real and imaginary part. That just doesn't, that's kind of sounds weird, but when you get into discrete time signal processing and software-defined radio, then that becomes very commonplace. But most of the time this is what applies. So the symmetry applies, Fourier coefficients are conjugate symmetric, magnitudes at the positive and negative indices are equal, and the angles are equal and opposite. And then we have these other nice properties that you learned about a while back. Waveform symmetry conditions. An even function means it's even about that t is equal to 0, so that means the Fourier coefficients are purely real. And if it's an odd function, so the function is the negative of itself on the negative time axes, then it's purely imaginary. And then the third in this collection of symmetry properties is odd half-wave symmetry, and that's kind of the classical, square wave thing. That'd be the odd half-wave symmetry. So you have half, that would be like at A, and then you have minus t over 2, and minus A the square wave doesn't have to be symmetrical about the amplitude axis. Really to have the odd half-wave symmetry property hold, but everything holds under this condition. And I'll explain the difference because there's a couple of extra theorems that I've added, properties of Fourier series coefficients, that kind of explain how you can work with this. But still, for the square wave, it does have to be minus and plus a, because according to the odd half-wave symmetry, this and this have to be equal and opposite in sign. And when that's true, then x of n is equal to 0 for n even. That means n is equal to 0, which is the DC component, will of necessity have to be equal to 0. But like I said, the odd half-wave property holds with the exception of the n is equal to 0. If we take the waveform and just raise it up or lower it down, we're just simply doing what? We're going to change the DC value or the average value, right? The way it stands now, the average value is 0. But the odd half-wave properties still hold with the exception of the DC value, even if it's up on a pedestal. And I'm sort of thinking of a logic 1 0 1 0 pattern, and a logic gate would come out at like, what's CMOS logic levels? I know what TTL is because that's what I grew up with, but CMOS would be like point something up to, what if it's 3.3 volt logic, it rises up to about 3 volts or something like that.
Like 0.7 to 3.
Yeah. So if that was a 1 0 1 0 pattern, that would satisfy odd half wave, not perfect according to this theorem, but it would be only deviate from the DC component, because the waveform has a positive DC value because it's averaging somewhere above the axes. I have a proof thrown up in here. It's just interesting to read about. When I was in school, we spent a lot of time on these things. We did a lot of Fourier coefficient analysis. It was miserable at times. I don't think you guys are being dragged through the mud nearly like I was. And I'm not saying that you're not hardy and everything like that. It's just we have other things to do, so let's not go after things that aren't super vital. When I wrote my dummies book, the editor said, you don't need to talk about Fourier series because nobody cares about Fourier series. And I said, I disagree. I wanted to have a chapter on Fourier series, and so I got to have it. When you learned about it in 2610, you were just an infant, right? You were just learning about signals and systems. And what do you remember? Was it pleasant, or was it kind of a not pleasant thing?
I did that class over summer and I forgot everything since.
Well, my experience with teaching students for many years is Fourier series is like the thing that people hate the most or dislike the most. Fourier transform, better. Fourier series, not so much. The good news is, though, we're going to have this means of dealing with Fourier series through the Fourier transform in a particular theorem, so it makes life a lot more palatable in terms of line spectra. And Lab 2 really dwells on that a lot, so those of you that are in the lab are going to hopefully get more comfortable with it and say, this isn't really all that bad. It's actually not bad at all. So it's still tedious. There's also other forms. I'm not really going to talk about the other forms. They're out there. I learned about them, and I think about them because I can dredge them out of my brain, but complex exponential is perfectly good for this class. You don't have to have the sine and the cosine form. The only thing that that I think is nice to deal with is this form right here. But this form follows immediately from the symmetry property and the expansion in terms of complex exponential coefficients. So that shouldn't come as any surprise to you, right? You always have an x of n and an x of minus n, and if they're conjugate symmetric, you can pull out and use Euler's identity to create this result right here. So you can always reduce it down to a magnitude and an angle and a cosine, which, by the way, if you look at this, you should say, I just did this on the quiz. I asked you to do the one-sided line spectra. So the one-sided line spectra takes the the DC term and treats it by itself, and then this 2 times xn is that doubling that you have going on in the positive frequency axis. So in my mind, I like to think that when you're doing a one-sided spectra, which is what the spectrum analyzer displays in the lab, you're actually working with this form of the Fourier series. And it's not really bizarre at all, is it? It seems very natural. You have a magnitude and a phase associated with the positive Fourier coefficients. And I have a line spectra plotting function that's in my Python module SIGSYS, so it plots line spectra and it uses that information. Parseval's theorem is also another nice thing to at least know of, and that is that the average power, which is what we talked about last time for a periodic signal, is that if you do it in terms of Fourier coefficients, it's just summing up all of the Fourier coefficients. And this idea will come up a little bit when we're looking at modulation theory too, and power contained in a band of frequencies. The second line there is kind of harkens back to the symmetry conditions, just saying that you have the power in DC and this would be the AC power. Does that make sense? I know when you first learn about power in circuits, it just seems, in my recollection, it seems kind of foreign. You talk about the AC power, and then when you do DC circuits, you talk about DC power. And in my thinking back, it doesn't seem like the two get brought together. Is that true? Do you have that impression that it's like this is this and this is that? But in reality, they're not separate. They are together, because when you learn about electronics, you do have a bias network around a device, which is DC, and then you also have AC power when you amplify a signal or something. Line spectra also follows very naturally in the Fourier series domain, because we already talked about double-sided spectra, so that follows immediately from the Fourier coefficients. You get the magnitude and the phase from the xn coefficient in the two-sided domain, and then this other form, what I call the magnitude and phase form, which has it as a one-sided spectrum. You just get it by doubling the amplitudes, but the phases are the phases of the positive, n greater than or equal to 1 coefficients. The function I have in the Python module plots one-sided or two-sided once you give it information. This is another example of just finding Fourier coefficients and then plotting the line spectra. So we kind of did this already. It's just, again, by inspection. Use a trig identity this time to expand into a 1/2 plus 1/2 cosine of twice the argument. And then you can immediately use Euler's identity to drop down to the complex sinusoid, or you could just stop off and pull out that form on the right matches exactly the single-sided spectrum form. And then you could, delve into the two-sided if you wanted to. Again, it's just the uniqueness property. So I haven't done any Fourier coefficient analysis yet, but this example is in the notes because this is a classical analysis problem. It occurs in 2610. If you were to go look at my notes on my website for 2610, and you look in chapter 3, is that right? That's where you start Fourier series. You would see this exact problem in there, because it's kind of a classical pulse train. What is the spectrum? What are the Fourier coefficients of it? And you're going to do this in lab 2 very kind of rigorously. You're going to recall this analysis, and then you're going to take measurements on the analyzer, and you're just going to validate that everything works out beautifully. And I don't know, I'm a person that's hands-on because I like to have that closure. I like the math. I also like to see the closure of taking measurements, maybe a simulation, and it works out beautifully. So here is the pulse train, amplitude of A, the so-called duty cycle. The period of time out of the total period t naught that it's on is tau. What's not showing up in here, and what is a theorem that we'll be talking about just a few minutes, is it's also possible to say that the pulse is at little t naught, and then this will be tau plus little t naught, and then this will be t naught plus little t naught. So in other words, you can just arbitrarily orient the waveform at a offset of little t naught. But rather than complicating this initial analysis, we have a theorem that will manage that later. It's the delay theorem for Fourier series, which you already know there's a delay theorem for Fourier transform, so it goes hand in hand with that. So in order to do the analysis on this, the analysis equation says we have to go through and get the Fourier coefficients for the pulse train, and we just need to take one period. So I'm going to take a period that essentially just sits right in here. That's the period I'm choosing. I could start at 0. I could essentially move that over, and I could say I'm going to start right here and just stop right there. That's probably what you're thinking. Why don't you just start at 0 and go to tau, and then you have a non-zero integrand, which I have here, and then the remaining integrand, the second integral, would be from tau, tau to t naught, and that's going to be 0 because the integrand is 0, right? So integrate that, plug in the limits, and then you quickly get it into this form. It's easy to get right here, but most of us aren't content, or I'm not content to just say, that's it, I want to leave it in that kind of ugly looking form. It's better to go the extra miles on this and do some trig manipulation into a form that Euler's identity can work with. So the trick is to factor out half the argument So 1/2 of the exponent is factored out, and then in order to compensate for that, you have to put in a positive of that exponent on the first term. The 1 gets a term added in there to make it cancel out, and then we have the setup for a sine. So we have a sine function defined from the e to the plus j minus e to the minus j, and then we can factor out a 2j from the bottom right in here, and then that becomes sine, and then we're left over with the other pieces in the denominator, and so we get a sine x over x, or actually a sine pi x over pi x. So in the substitution, that's what x is. And that's a special function which communications engineers like to use for modeling purposes, a sinc function, which you've seen before. MATLAB has a sinc function. Python's NumPy has a sinc function. Mathematica has one. Virtually any language you might think of will have a sinc function. And you're probably pretty used to that idea, right? What are some of the uglinesses you might remember about sinc functions? Once you have it, it's like, it's cool, but what's something that you might remember about the sinc function just as it stands right there? Two things I think about. Number one, if you try to evaluate it at its argument equal to 0, what do you have to do to evaluate it? Yeah, L'Hopital's rule, right? You have to take a limit because you have 0 over 0, so you take derivative top and bottom and then reevaluate the limit until you get something that's determinant. So that's one big property. The second big property is that the sinc function has periodic zeros in it. So it goes through 0 at periods of the argument. And that's just because of the sine function. The sine of an odd multiple of pi is always going to be 0, right? So it can be pi, 2 pi, well, what am I thinking of? I'm getting myself confused, I guess, on something. It's going to be 0, sine of, yeah, those multiples, 1, 2, 3, 4, 5, 6, 7, 8, 9. So any integer value for x will evaluate to 0. So when you finally put that together, you get this nice formula for the Fourier coefficient in terms of the sinc function. And then we can go ahead and plot the sinc function if we want to. What I did here in the notes is I used the line spectra plotting function that I have built into the SIGSYS module and plotted a particular value. The magnitude of the coefficient is easy. The phase is messy, is all I can say. I don't really, for this class, I don't want you to be worried about plotting the phase because it is messy. It's got tedious nature to it because what makes it so tedious is the fact that the phase is that argument. So that's part 1 of the phase. But then this changes sign. So that's what makes it kind of messy, because when that changes sign, then you have to throw in 180 degrees of phase, and then you have to decide whether or not you want to say it is 180 or minus 180. And generally when things get plotted, they like to plot them nice and odd symmetrical looking, but that's just because of the angle as being a modulo 2 pi function. So that's what makes it messy though. But I do have a nice picture in here. I have the code that goes with it. And at this point, I'm just going to jump over to this notebook since it's right here in the notebook. So I have this line spectral plotting example. Just going to turn off that sidebar. So I have this function called line spectra, and I don't know if I had to restart this notebook or not. Let's just see if it's alive, and it's not. Wait a minute, I haven't run this function. So here I just defined a pulse train function for plotting a pulse train. But really I only need one period. So in this function if you want to plot a picture of a pulse train, I just have it create data that plots n periods of it, and it returns t and x. If I want to actually get that plot, I guess I have it right here. So there's two values of a pulse train. I plotted the pulse train, and then I plotted 1 minus the pulse train over here. So I plotted it twice, actually. And the reason why I did that is because there's a homework problem. I haven't decided if I'm going to assign it. And that homework problem deals with this aspect, the fact that those two waveforms have similarities. It turns out that their Fourier coefficients, the magnitude of the Fourier coefficients is identical for those two waveforms with the exception of the DC component. Is that believable? Duty cycle is the same. One goes down, one goes up. One has a small average value. Which one has the large average value? Okay. But those are all things that a theorem I'm going to show you actually deals with. So the Fourier coefficients are identical. And if I just use the equation we just went through and have that written here in the notebook and then plot the spectra. So in order to plot the spectra with my spectrum plotting function, line spectra, I need to load it with Fourier coefficients. So I load them in this array, which is going to range from 0 up to the 25th harmonic. Python always stops one index less. That's just the way it works because it starts at index 0. So I just put a +1 on there so it goes all the way up to 25. Those get loaded into my function right here. I put in a set of frequencies. I can put in just the index to assume that the fundamental is 1 Hertz, but I could put in other numbers. And then I get to specify, do I want magnitude or do I want angle? So the help is right here. It tells you what it can do. Do magnitude in dB. I actually adapted this function for use in the lab number 2 for doing line spectra plotting in dBm, just to make it match what you see on the spectrum analyzer when you're in the lab. So it actually works out pretty nice. So let's just do that plot. So there is the pulse train that has duty cycle tau. So let's just check out this variation that I did here where one waveform is 1 minus the top waveform. So let's just answer a kind of a dummies question. What happens if I modify this waveform? And I'm trying to remember, how did I do that? I guess I have to get a new coefficients formula, so maybe I don't want to do that right now. But yeah, it relies on my theorem, so I'm not going to do it right now. I think I might have another example of this. But there's the angle plot, and a few other things are in here. I just want to move on unless you want to ask me some questions. Looking at the time here. So another thing we can go off into doing, not super essential, but I do have a discussion of this because I have functions for doing that in the notebook. And these can be useful in homework problems where you have to actually do a Fourier expansion, and then you want to just represent one period, and you say, let me have the computer numerically find the Fourier coefficients, because surely a computer can find Fourier coefficients because it's a numerical integral. It turns out the fast Fourier transform can do that for us very exactly. And you probably are saying FFT because you've seen the FFT, I think, in 3205, right? Maybe, maybe not. Well, if you take the synthesis or analysis equation, which is this guy right here, for the Fourier coefficients, and then you approximate it as a sum of sample values of the waveform, using n sample values, and this piece over here is in the numerical integral, that's delta t. So remember calculus and the Riemann integral that you learn about in calculus. You're just going to create rectangular partitions, and then you take the limit, and that forms the integral. So this is going backwards on that, saying let's approximate the integral as a sum of rectangular areas of rectangular partitions. And we just have to put a delta t in there. So I do that, and then I rearrange that slightly down below because I have that 2 pi f naught t naught is just 2 pi. And then I get it into this form here, and this is very close to the fast Fourier transform of a sequence of samples. So I talk about that here and then just say it's the discrete Fourier transform, which efficiently is done with an FFT. So bottom line is I say this is set as an approximation because it's just approximating an integral with n partitions. But you should see that if I make n larger, I'm going to have finer and finer partitions, so my numerical integral should become more accurate. Make sense? So then do a little bit more modeling and then summarize it for a real signal. It's we can take into account the symmetry property, and then this is what it comes down to. And in Python, when you've got NumPy loaded, you have access to a whole collection of FFTs by going FFT.FFT. So that would be true over here. You just add a cell below that. Then if I type dot again and hit tab, I should get the listing of all the functions. Well, actually, I want to do it like this. So those are all the different functions that are available inside the FFT submodule of NumPy. And in particular, FFT is just the forward FFT in one dimension, or at least the way we can make use of it right here. I'm also showing you how it's a little bit different to access than it would be in MATLAB. In MATLAB, you just type FFT and you could get access to it. Here you have to sort of go into a subdirectory with the dot operator to say it's the submodule FFT, and then its functions inside of it. And when you do something like that, it's kind of nice to just, when you type the dot, you can hit the tab key and you can see what all the different functions are in the module. And obviously, there's an IFFT down below here, and that's the inverse fast Fourier transform. We use those a little bit in modern DSP right at the end of the semester. At any rate, so I took an example of a waveform to do some numerical modeling with, and I did this because it's something that would be kind of ugly to do to get the exact Fourier integral. You'd have to take this period of t naught and you'd have to integrate, well, how many integrals would you end up having to do to get the Fourier coefficients? You'd break this down, and how many sub-integrals would you have? Which jumps off the page at you. If you had to find analysis of this trapezoid, how many integrals would be involved for each?
You do it 2 and 3. That's what you have shown.
You have to do it for 3, the way I see it. So you'd go 0.
Symmetry, double those.
I'm not sure about that because of the fact that it's sloping up and sloping down. I didn't do that though. I was lazy. I did my numerical algorithm on this. And why I chose this pulse is I said, okay, in logic circuits, or logic circuit electronics, you know that the rise and fall time on a logic family is not instantaneous, right? If you zoom in on the scope, you see it rises up, falls down. Let's just get an idea about what sort of rise and fall times a logic family has, and how is that going to alter the harmonic content of, say, a clock waveform that has a finite rise and fall time. Why do I care about that? Well, I might be intrigued by the fact that in my laptop I know I have a 3 gigahertz CPU, and I'm thinking about how much energy is radiating at harmonics of 3 gigahertz up at really high frequencies, and what are some shielding issues and what might be some potential interference issues. So I know that the clock edges are not 0 rise time, so my intuition says that if I rise up in a finite amount of time, that should make the higher harmonics fall off faster in amplitude. Is that intuition kind of in your brain? A fatter pulse, something that moves slower in time, is going to have less high frequency components, right? And sometimes it's better to actually slow down edges on a clock waveform. Most of the time we want fast edges because then timing is really accurate and precise, but 0 rise time clock edges would take more power in the gate logic, and it would radiate a lot more harmonics out there because it would have much slower roll off of the harmonics. And I know in the lab you started to observe that, those of you in the lab, that a square wave rolls off at a 1 over n factor, a triangle wave rolls off at a 1 over n squared. So trapezoid is going to be somewhere between 1 over n and 1 over n squared, is what I'm theorizing. So I plugged that in. I defined the waveform numerically so that I could then come along and take the FFT of it for a particular trapezoidal pulse shape, and then I get back the Fourier coefficients up there at the top, capital XP, and then I can plot the line spectra. And I just picked some ratios. I said the average pulse width of this thing is 1/8 in normalized time, where the period is 1 second. So it's a duty cycle of about 1/8 on average. And then I said that the rise and fall time is 1/20th of the period. And I plotted the result using the line spectral plotting function of the roll-off. And I know that it's got a sinc function kind of behavior, but it's not just a simple sinc function. But the thing that I noticed, and I don't really prove it here, I just say the side lobes are smaller than the ideal pulse train because it's got finite rise and fall time. And then I took a second kind of really extreme example, and this would be a scenario where you might increase the clock rate, and now the rise and fall time is really, you're pushing the limits because the logic family is getting close to its maximum clocking rate because it has rise and fall time that's limiting the ability to discern ones and zeros. So here, the side lobes are even smaller because the waveform is spending more time rising up and falling down. And these are the types of things that are interesting that you can do with signal modeling and trying to analyze a logic circuit problem or a radiation problem. You know, how much harmonics you're emitting. The FCC might say you've got to put more shielding around a PC or something. I mean, I personally was fearful when clock speeds went over a gigahertz. It's like, wait a minute, we're radiating all kinds of energy out of our computers. Isn't that going to cause issues for other wireless devices, like up at, well, I can't say 2.4 gigahertz because we're mostly above that now with the fundamental of the clock frequency, but does that kind of pop into your mind, or you're not yet thinking about how just understanding radiation effects from signaling in electronics could be desensitizing or doing something like that? I still don't have it figured out. The clocks are high, but then the harmonics are just way up there. So I think I go through that in the notebook over here. I define that and then do some plots of it in here. So first I have to define, I wrote a function to generate the trapezoidal pulse, and then this exercises it and creates the waveforms that we were just talking about. Just the beginning of playing around in the types of things you can do with playing around. So last thing in Fourier series, just as the foundations go, is what are some additional theorems on Fourier series coefficients, and these are pretty handy, I think. They might be homework problems in the book that Dr. Zemer put up, but he didn't put them in the lecture notes per se, or the lecture, I mean the regular part of the book. One of the things I guess I'll point out quickly, though, is some of you, like Chris, you bumped into the drill problems. If you go just before the drill problems in the book, you'll find that he's got a chapter summary, and that is actually pretty handy when it comes time to study and review. He was my mentor and advisor. He writes a fairly condensed book. It's not really fat, but he does include, I think, some nice usability features in his book. Some books just give you, well, what's a good example? What's a book that you can think of that's just overloaded with pages?
The Bible.
I'm talking about an engineering book. The Bible's got a lot of pages, but there's a lot of information there. But I'm thinking of an engineering book. What's an engineering book that is just massive that you use?
Electronics.
Yeah, electronics. I think that is just, it's like that, isn't it?
Yeah.
One and two.
When I took electronics a long time ago, it was the fattest book I had, and it's gotten fatter. It's probably about 1.5 times as thick as it was when I was in school. It's huge. I wouldn't want to carry one of those around regularly. So at any rate, some nice little concise info. This first property is, it says, suppose you know something about x of t in terms of its Fourier coefficients, and there is a nice table in the book. That table is also in your crib sheet. What are the Fourier coefficients of a waveform that's closely related to it, one that's linearly transformed? We add an offset onto it to raise or lower the waveform, and then we gain scale it by b. So the Fourier coefficients now on the new waveform end up being, the DC component is a plus b times the original DC component, and intuitively that makes sense. And the non-DC components just get scaled by b. And the proof is right down here. But that's a real, you probably have thought that. I can ask you this question on a quiz problem next week or on an exam, and it's not, you don't have to prove anything. You now just say, I know this is true. It made sense to you before, and now we have the proof, so now you're good to go. Or I could turn this around, though, on a exam, as I could say, prove this is true, right? Because this proof doesn't look particularly complicated, but it's common sense, though, isn't it? So that's a really nice one, I think. Likewise, the time delay theorem for Fourier coefficients is like the one for Fourier transforms. If you take a waveform and delay it by t0 seconds, what does that do to the waveform's Fourier coefficients? Well, you just plug that in, and I'm using the time average operator notation for convenience, and then you carry that through, and the bottom line is just the result right here. It says that it's the original Fourier coefficient, and then all that changes is the angle associated with the Fourier coefficient picks up that t0 factor. And when we get up to Fourier series or Fourier transforms, I mean, this will become just f, and that will be that theorem from Fourier transforms that would say y of f is equal to x of f times e to the minus j 2 pi f t0. So this is like the sampled frequency version because we're talking about periodic waveforms. So we have n f naught there instead. So another big moral to this story is if you're looking on the spectrum analyzer and your waveform gets shifted, back and forth, and you can't really control that from the function generator, the magnitude spectra is totally unimpacted by the time offset. And that's true here, because we take the magnitude and the t0 doesn't factor in. Now, with that said, though, if we bring two periodic signals together, one arrives at 0 seconds and one arrives at a half second later or something, and they add together, but they're both the same periodic waveform, just arriving differently, then we're going to have constructive and destructive interference potentialities. We'll have a Fourier coefficient for the sum of these two identical waveforms, but then we'll have to use these complex exponentials to actually be part of the phase combining of the two signals. And then any amplitude that might be in there would be present. So I'm mentioning that because in multipath communications, that's exactly what happens. Rays arrive at my body, bouncing off different objects in the room, and all of you have experienced this with your cell phone. You know what I'm talking about? You're standing here, you have one bar, you move a few feet away, and what happens? All of a sudden, it increases a lot because the wavelengths are so short. Just a small amount of motion, and that combining of those identical waveforms is now phase shift. I mean, they're getting this time delay kind of a property. Does anybody ever do that a lot? I mean, I've done it before. I know in my house, because I don't have very good AT&T wireless, you got to move around a little bit sometimes to get the bars to come up. Everybody in here is probably bar sensitive. I mean, it's a weird thing about our society, but when we pull out our device, I've got 3 bars on my phone right now, and mine's on AT&T. Okay, so that covers that. Keep those properties in mind when you're working problems. Simplify, don't reinvent the wheel. Use the tables of the Fourier coefficients for certain types of waveforms. Don't invent the wheel. Soon, though, we'll be developing a theorem, and I'll just kind of dial up there. I'm going through Fourier transforms right now, but I'm just going to dial up to this theorem, which is, it comes under the Fourier transform and the limit idea, but what we're headed for is, let's see, this theorem right here, and this shows up in Lab 2 a lot. It says if we can look at one pulse associated with a periodic signal And we assume then that a superposition of time-shifted pulses, which is on the left side here, forms our periodic signal. If we want to get a spectrum of that signal in the Fourier context, which is just sort of making things, all spectra look like they're in Fourier transforms, except now the line spectra that we've just been talking about gets represented using delta functions to place the spectral lines. But the big key here is that the Fourier coefficients will end up being Fs, which is 1 over the period times the Fourier transform of 1 period, but F is replaced by sampling at n times Fs. Now this will take some while to unpack when we get here, but this is your life in the Fourier series domain, viewing it as a Fourier transform. So you just have to be able to Fourier transform 1 period of a waveform. Lab 2 will kind of emphasize this. Does this seem cool, or does this seem, maybe you're saying, I wish I never had Fourier series in my life. I don't want to worry about periodic waveforms, but radar signals are periodic frequently. Com signals can have periodic components, so you can't escape them. And it's cool, though, that the Fourier transform can manage them for us. And I think that should be appealing, because I already said most students don't like Fourier series. And this is a way of making it more manageable. And we'll come back to this for sure. So now we move into the Fourier transform, which hopefully, for the few minutes that are left, we'll get started on it. And hopefully you like the Fourier transform better, but it seems like in our current curriculum, it's hard to get enough time on the Fourier transform. I know from teaching 2610 that it was hard to do it in that class with the time allocated. And the next class that you get up time on the Fourier transform is 3205. And, right? Dr. Tromboli's class or Dr. Semiari taught it for him last semester. But those of you that just completed it recently did spend time on more time on the Fourier transform in that class. True or false? Yeah. Did it sink in, do you think? We're going to find out. We're now going to find out. It's like the most important thing now in this class is to move forward and get that settled in a better way, and then be able to use it for everything the rest of the semester. So Fourier series will come back, but they're going to be brought underneath the umbrella of Fourier transform and the limit. But the Fourier transform is just inescapable. It is bread and butter for a communications engineer to just get it. And it has, there's basic theorems that we use all the time. So it provides frequency domain representation for aperiodic signals, whereas Fourier series was for periodic signals. But this third bullet, though, is what I've been alluding to. Ultimately, we'll be able to bring the periodic signals in under the transform and the limit idea. And there's a mathematical way that I put in the dummies book that Dr. Zemer taught me ages ago, that where you take the limit as the period goes to infinity in a periodic signal, and then the xn becomes the x of f, and then you have the Fourier transform. So what he taught me is that first Fourier series, because then when you do this limit, then you get Fourier transform. Because if you take a periodic signal and you think of making the period really, really big, all those other images kind of go way out there, and you're just looking at one period. And that's how the Fourier transform came into being, or gets put up. I'm kind of waffling the time away, but Fourier shows up in some other disciplines really close by, and that is if you take partial differential equations, or if you really love electromagnetics and certain semiconductor device properties, but electromagnetics was my minor. So certain types of electromagnetic geometry configurations are partial differential equations, and you can solve those equations using Fourier series, believe it or not. Fourier series methods will solve for fields, electric potential and magnetic potential with Fourier techniques, boundary value problem solving. So Fourier is around there, It's also used in other mechanical engineering subjects too. So we all enjoy this to the same extent. I like the waveforms case though a lot myself, but I did take boundary value problem solving with Fourier series, and I was pretty impressed by that. And if you play guitar, you'd be impressed by that too, because a guitar string is a fundamental model. When you pluck the guitar string, it produces overtones, and that's because of the mechanical distribution of mass in that string. And when you solve the boundary value problem for the vibration and then the modes it sets up, the harmonics, which we get to hear, it's all related back to Fourier analysis too. And that's pretty exciting. I play bass trombone, and my instrument produces lots of overtones too. I don't know how to analyze my overtones in the same way, but the guitar string is a kind of a classical one for analyzing overtones and harmonics. So sufficient conditions, well, this is the inverse and forward Fourier transform. I guess I'm going to have to stop here for the day, but what's the feature of what we use in this class is that we're going to use F. We're not going to use omega, which is 2 pi f. So I think in the 3205 book you used omega. Is that true?
Yeah.
So you're going to have to get reprogrammed to use F. Control systems people, I think, are okay with omega. They're the other part of the signals and systems world that we're part of here. But communications engineers like to use F because that's hertz, and that tells us where the frequencies of interest are in the spectrum for the radio and all the other signals. So, and the other thing, besides that being the overriding selling factor, there's a certain thing I like about the frequency domain Fourier transform pair. It has this nice symmetry to it. You don't have that 1 over 2 pi sitting in one of them. You're noticing that? So learn to love this Fourier transform. There's actually like 3 popular Fourier transform setups. One would be this one. The other one is 1 over 2 pi in one of the two. And then another one is 1 over the square root of 2 pi in both of them. So that's a third one. I think physics uses that one. You can believe that though, right? Each group of scientists, engineers has to have their own favorite. So this is the favorite one for comms people though. And we'll launch into symmetry properties, energy spectral density, all that kind of stuff. But this will be showing up in some of the homework problems for the next assignment. I'm going to stick to time. I've got 2 appointments from outside of this class that are right on deck when I get up there. But if you want to hang out, you can be 3 and 4 and 5, whoever wants to visit me.
You gonna post homework tonight?
After my handbells practice at my church, I guess I'm going to go for it. But yeah, I'm going to get on it. Push them up there, you mean? Or do you want the solutions?
The solutions are up. I meant homework assignment 2.
Yeah, I'll get that up. Well, the solutions are not completely up there. You're going to have the solutions for the missing problems.
Not really worried about that. I already turned my homework in.
Okay. That's coming, though. Yeah.
No, I'm more worried about getting started on the next assignment.
Yeah. I'll put that as a priority then, since you're voting that way.